Hello James, welcome back to another video. In this video, we'll be discussing the previous year BITSAT questions from the chapter of wave optics. Now, with this chapter, we'll be taking the final few steps towards our A series. Believe me or not, we have almost covered up all the chapters, the previous year questions from all the chapters, and you can check out the links to the playlist in the description box of this video if you have missed any one of those. Okay. So after this video, only one chapter will be left, which is ray optics, and I'm pretty sure we'll be able to cover it up within this February, and in March we'll start something new for you. Okay, so stay tuned and let's begin with this video. So let's begin with the super easy category like we always do for A series. So here is question 1 from 2008. So here we have a YDSA experiment going on, and you are given the following data that the fringe width is, not the fringe width, the distance between the two slits is 0.1 millimeters. The wavelength of the light used is this much. The distance between the screen and the slits is this. You are supposed to tell what is the fringe width. Such a straightforward question, right? Because you know that fringe width is simply given as lambda capital D by small d, right? So it's a direct formula based question. You are just supposed to substitute the values over here and get your answer, right? So that's why it's from the super easy category. Okay, so let's substitute. Lambda is 600 nanometers, that is 10 to the power minus 9. Capital D is 1 meters, and this is 0.1 millimeter. Okay, I can write that as 10 to the power minus 4 meter, right? Because millimeter is 10 to the power minus 3 meter, and into 0.1 that will become 10 to the power minus 4, right? So this and this will cancel and give you 600 into 10 to the power minus 5, and again two zeros we have, so 6 into 10 to the power minus 3. Okay, these two zeros will cancel with that. Okay, so we have 6 into 10 to the power minus 3. This is in meters, or you can write 6 millimeters, right? Because 10 to the power minus 3 meter is millimeter, 1 millimeter. Okay, so option B, 6 millimeters is the correct choice over here. Okay, so you were just supposed to know the formula and substitute to get your answer. Okay, we'll raise up the level. Don't worry, these are questions from the super easy category. Okay, now here is a question. This is question 2 from 2018. Okay, here you are supposed to find third order maxima. In this diagram, you are given different fringes and they are labeled. Okay, and the second fringe is given as central bright. Okay, and from there you are supposed to find where is the third order maxima. Okay, so basically the third bright spot. Okay, so this is the central maxima, right? This is the central bright spot. Okay, so here we'll have the dark spot, here also we'll have the dark fringe, right? So on both sides of the central maxima you'll have the dark fringes, right? And then you'll have the first bright over here. Okay, I'll write it. So this is the first dark, this is the first bright, then we have the second dark, then we have the second bright. So basically dark, bright, okay, or bright, dark, again bright, then we have third dark, and finally we have third bright. Okay, so that is what we are supposed to find. Third maxima means third bright spot, and where is that? That is on the 5th position, right? So option D, 5 is the correct choice over here. Okay, so basically using your logic you are supposed to solve this question, nothing much mathematical over there. Okay, so let's come to question number 3 now. Here you are conducting a YDSA experiment 3 times, once with a red color, a red light, blue light, and then green light. Okay, and then you notice the fringe width for each of this experiment. Okay, this is the fringe width for red, this is the one for green, and this is this is the one for blue, this is the one for green, and this is the one for red. Okay, so you are supposed to tell what is the relation between this fringe width. Okay, just now we saw that beta is directly proportional to lambda, right? For the same setup. Okay, we are not changing the slit width. Okay, we are not changing the distance between the two slits, we are also not changing the distance from the screen, right? So we are not changing capital D or small d, so you can say beta is directly proportional to lambda. Okay, and if you see, red has the highest wavelength, right? Red has the highest, then we'll have green and then blue. Okay, so basically VIBGYOR, you can remember. Okay, red has the highest wavelength. Okay, it's on the extreme right, then here in this three colors we'll have green, and then finally blue. Okay, so the one with the highest wavelength will have highest fringe width. Okay, so basically red will have the highest, then we'll have green, and then blue. Okay, red, green, blue, red, green, blue, option D. Okay, so fringe width of red will be the highest, then green, and then blue. Okay, so basically there is a direct relationship between the your wavelengths and the fringe width. Right, now finally, angular size of central maxima in diffraction. Now this is directly a theory based question. You are supposed to directly know the answer. Basically you can write the fringe width, I can denote it as theta, suppose, or w, whatever you use. So it is lambda by a. Okay, for any other fringe. Okay, this is diffraction, and this is for any other fringe. Okay, not the central one. You'll know that the central one is 2 times as big as the others, right? So it will become 2 times of this value. Okay, so for the central bright one, it is 2 times lambda by a. Okay, so directly theory based question. So 2 lambda by a is the correct choice over here. Okay, so with that we end up with the 4 questions. Let's I think these were the questions from the super easy category. Let's move to the easy category now. Okay, so question 5 and 6 over here from the easy category now. So in question 5 from 2006, we are supposed to tell, so this is a diffraction experiment happening over here, and we are given that the angular positioning at 30 degrees, we have the first minima. Okay, so at an angular position of 30 degrees, we have the first minima forming. You are supposed to tell what is the width of your slit. Okay, of course, it's a single slit experiment, so D is the slit of the width of the slit, not slit of the width. Okay, so A or D, whatever letter you use for it. So from here, actually, you can get a clue. You are told about D. Okay, you are asked about D, and you are given theta. Okay, so you can use the relation delta x equals D sine theta, where delta x is the path difference, right? And D is something which you are supposed to find. Sine theta we can find. Okay, now what about the path difference? Okay, now in case of diffraction for minimas, what is the path difference? It's given as n lambda. Okay, of course it's opposite for your diffraction and interference. So for minima you'll have n lambda for diffraction, but for maxima in interference you'll have n lambda. I know it's a bit confusing, but you have to remember that uh, your interference and diffraction are in a way opposite. Okay, not completely, but in a way. Okay, so the path difference for minima in case of your diffraction is n lambda. Okay, now it's the first minima, so we'll substitute n as 1, so we'll get lambda is equal to d sine theta. Of course, some of you might know it directly that for the first minima, the path difference in diffraction should be lambda. Okay, so lambda equals d sine theta. Okay, so path difference is lambda. Now lambda is given as 5000 angstroms. Okay, so 5000 into 10 to the power minus 10, I can write it that way. Sine 30 is half, so it will be d by 2. Okay, I can bring this 2 to the other side, multiply it. Okay, 2 into 5000, that is 10,000, 10 to the power 4. Okay, and we have this. Now this distance is in meters, right? So we'll get 10 to the power minus 6 d. Okay, this is in meters. We can convert it in centimeters. The answers are in centimeters. So I'll write it as 10 to the power minus 2 into 10 to the power minus 4. Okay, so this 10 to the power minus 2 meters will become centimeter. Okay, so this will become centimeter. So this is 10 to the power minus 4 centimeters. Okay, so the answer should be 10 to the power minus 4 centimeter. I think this one. Okay, this one, if you simplify 10 into 10 to the power minus 5, that will become 10 to the minus 4, right? So option B is the correct choice over here. Okay, let's come to question number 6. Here you are given the numerical aperture of a telescope, and you are also given the wavelength which is used to see. Okay, you are supposed to tell what is the limit of resolution. Now this is also an important topic for BITSAT. You'll see this topic in the last few pages of your NCERT. So if you find this topic difficult, okay, just remember the formulas. Okay, so those are important for your BITSAT. Okay, questions are asked from that part too. Okay, so just remembers the formula over there. Okay, so here the limit of resolution basically will be given as 0.61 lambda by a. Okay, you are supposed to remember this formula. So let's substitute the values. It's directly a formula based question, so substitute the values, get the answer. 0.61 into your lambda is 600 nanometers into 10 to the power minus 9 meters, and what is a is 0.12. Okay, actually you can treat this 0.61 as 6 only, so 0.6 into 6 into 10 to the power minus 7, cancel some of this. 12 into 10 to the power minus 2, again you can take this as 6 into 6 into 10 to the power, this will be 10 to the power minus 8, and again plus 2, that will be minus 6. Okay, just quick maths over here, and then you'll have 12, 6 2s are 12, and you'll have 3. Okay, 2 3s are 6, so 3 into 10 to the power minus 6, which is 3 micrometer. Option D, 3 micrometer is the correct choice over here. Okay, so remember the formulas from the last few pages of your NCERT, limit of resolution, resolving power, those topics. Okay, those are also important. Let's move to the next set of questions now. So question 7 and 8 over here, still in the easy category. So question 7 from 2011, here we have a YDSC setup. We are given small d, capital D. We are supposed to find lambda, and we are also told one extra thing, that is the distance between the fifth minima and the first maxima is 7 millimeters. Okay, so basically if we have a screen over here, central bright over here, first maxima over here, so we have the dark spot, dark fringe in between them, and then we have the first bright fringe, and somewhere over here suppose we have the fifth minima, okay, or the fifth dark fringe. Okay, so basically the distance between these two, the fifth minima and the first maxima is 7 millimeters. Okay, now we can write this in a formula way, so I'll write y is equal to 7. Okay, so the distance between them basically is 5 Wi-Fi D, this entire distance minus this, right? You can write this 7 millimeters. I'll directly write 7, the 7 millimeters as this entire distance, which is the distance of the fifth dark fringe minus the distance of the first bright fringe from the central maxima. Okay, so that is what I'm writing over here. Okay, so that, okay, so 7 millimeters is equal to this distance minus this distance. Okay, I hope you can picture it. Now you can write the formula for them. Okay, so we have the fifth minima, so 2n minus 1 into lambda by 2. This is the formula for minima, general n. Okay, here we'll substitute n as 5 in the next step, and for maxima it's n lambda capital D by small d, right? And here we have to substitute n equals 1, first maxima, and here fifth minima. Okay, so 2 5s are 10, minus 1 is 9, so 9 by 2 lambda capital D by small d, and here n is 1, so lambda capital D by small d. You can take lambda capital D by small d common. 9 by 2 minus 1, 4.5 minus 1, 3.5, which is 7 by 2. Okay, so 7 by 2, and here we have 7 millimeters, right? So 7 into 10 to the power minus 3. 7 and 7 will get cancelled. We are supposed to find lambda. So lambda will be basically 10 to the power minus 3 into 2 times of small d. 2 times of small d is 0.15 millimeters. That is again 10 to the power minus 3 upon capital D, right? Capital D will come in the bottom. So capital D is 50 centimeters, 50 into 10 to the power minus 2. Okay, so what are we getting over here? Okay, so let's see. 2 into 0.515 is 0.3, and that this is 0.10 to the power minus 6, and here we'll have 50 into 10 to the power minus 2, so this and this can get cancelled as 10 to the power minus 4. And what can we do next? Okay, we'll shift one more decimal. I'll make this 3 into 10 to the power minus 5. Fine, and we have one more 10 to the power minus 6. Okay, fine. And 3 by 5, 3 by 5 is basically 0.6. So 6 into 10 to the power minus 7. Okay, this is in meters. We have our answers in nanometers. Okay, so we'll multiply 100 and also multiply 10 to the power minus 2 to balance it. So that will give us 600 into 10 to the power minus 9 meters, or this is basically nanometers, right? So 600 nanometers. Okay, so that is our answer. A lot of calculation, but yeah, 600 nanometers. Option D is the correct choice over here. Okay, let's come to our next question, which is question number 8. So here we have the two sources, the basically the two sources in YDSE. Okay, they have their intensities in the ratio 1:4. So we can take the intensity of S1 as I and the second as 4I. Okay, so basically if you take the ratio, it's 1:4, right? So we are assuming their intensities are I and 4I. Okay, so then you are supposed to find what is I max and I minimum respectively. Okay, now this is very simple because I max is basically you are supposed to know the formula under root of I1 plus under root of I2 the whole square, right? This is how I max is given. So under root of I1 is under root I plus under root of 4I, so that is 2 root I. Okay, 4 will come as out of the root as 2, so that is squared. So x plus 2x, that is 3x, right? So we can write this as 3 times of root I. Okay, treating root I as x. Okay, so x plus 2x will be 3x basically. Okay, so root 3I square, that is 9I. Okay, now what will be the minimum? The minimum formula is under root I1 minus under root I2 the whole square. Okay, so under root I1, so I1 we have as I, and I2 we have as under root 4I. So basically that is under root 2I. Okay, so you can actually make 2I minus I, okay, instead of making writing like this. But anyways, the negative is of no importance because we have squared it. So minus root uh, I1, I should say. Okay, so it's like x minus 2x, that is minus x. Okay, so that is squared. So we'll have I. So the minimum is I and the maximum is 9I. So maximum and minimum respectively. So 9I and I. Actually, if you see by common sense, this one is wrong because basically maximum cannot be less than minimum. Also, if you see this one is wrong, right? Maximum cannot be less than minimum. These are actual BITSAT options. Anyways, 9I is the maximum one and I is the minimum one. Okay, so that is our answer for question number 8. Let's move to the next question now. So question 9 over here. In this question, we are going to repeat the YDSE experiment twice. Once was not enough to make you mad. So anyways, you can also see that this question has repeated over the years 2013 and 2017 twice. Okay, just a coincidence. Anyways, so the first time that we are going to conduct the YDSE experiment, we are going to use a wavelength of 7,000 angstroms, and the second time we are going to use a wavelength of 5,000 angstroms. Okay. So when we conduct it for the first time, we get to know that the 10th maxima occurs at point P. Okay, and in second time, some nth maxima, okay, it occurs at point P. You are supposed to tell what is the value of this n. Okay, so basically, suppose you have the screen over here. First time when you conduct the experiment, here you have your central bright spot. Okay, so central maxima over here, and you have point P over here. Okay, so first in the first case, we have the 10th maxima over here, right? And in the second case, again at point P, we have some nth maxima. Of course, the number will change because for different wavelengths, the basically the fringe width changes, right? You know the relation between fringe width and wavelength, right? So for different wavelength, the fringe width will be different, and since the fringe width is different, the positioning of each fringe will be different, right? So here for the first one, we have the 10th fringe over here, okay, and for this one we might have some other fringe. Okay, so basically let's see. Okay, let's see what we find. Here if you see, y remains constant, right? The distance from the central maxima to point P is constant. So we can write the y in the first experiment is same as the y in the second experiment, right? It's basically the distance between central bright to the point P, okay, which is not changing, of course, right? It's the point P is same in both the experiments. Central bright will be formed at the same position, okay, irrespective of wavelength, okay. So this distance from the central bright to P is not changing. So y in the first experiment equals y to y2, which is in the second experiment, okay. Now y1 can be written as n lambda capital D by small d, right? We are considering maxima, so n lambda capital D by small d. Now it's for the first one, so n1 lambda 1, okay. D and d remains the same. We are not changing the setup, I told you, right? Of course, n will change because the fringe widths are changing, position is changing, okay. So here we'll have n2 lambda 2 capital D by small d, okay. This will cancel, this will cancel, and you have a classic equation, n1 lambda 1 equals n2 lambda 2. Actually, in fact, in this cases, you can remember this as a general formula, okay. n1 lambda 1 equals n2 lambda 2. When you don't change the setup, but you change the wavelengths, okay. So in that case, n1 lambda 1 equals n2 lambda 2, okay. Your wavelength and n are inversely proportional, okay. Now what we are supposed to find? N2, right? N1 we know, we have the 10th maxima n1, right? And lambda 1 for that is 7000 angstroms, okay. I'll keep everything in angstroms. On both sides it will get cancelled. We are supposed to find n2, which is n, okay. What is the fringe number, okay, that occurs over here? What is the maximum number that occurs at point P in experiment number 2? That is what we are supposed to find. And lambda 2, if you see, we have used a wavelength of 5000 angstroms, okay. So this will cancel. 5 2s are 10, 7 2s are 14, so n is nothing but 14. So option B, 14, is the correct choice over here. I hope you were able to understand this. It was pretty much simple, okay. n1 lambda 1 equals n2 lambda 2. Let's move to the next question. So question 10 and 11 over here, questions from polarization. So in question 10, we have an unpolarized light which is passing through two polaroids, okay. The angle between the pass axis of the two polaroids is 60 degree. You are supposed to tell what is the intensity of the light over here, okay, after passing through the two polaroids. Now it's very easy. You can directly see that I dash will be I naught by 2, right? So whenever an unpolarized light passes through one polaroid, the intensity basically reduces to half, okay. So it becomes half of the initial over here, okay, after passing through the first polaroid. Unpolarized light passing through a polaroid, the intensity falls to half of the original, okay. So I dash is I naught by 2, okay. Now what about the intensity after passing through the second polaroid? For that, we'll use Malus law. Malus law basically is I equals I naught cos square phi, okay. So I equals I naught cos square phi, okay. So I naught is basically the intensity which is going in that polaroid, in that particular polaroid. Here it's the polaroid number 2. Phi is of course the angle between the polaroids, okay, between the pass axis of the two polaroids. I is the intensity on the other side, okay. So here we'll use Malus law. So I double dash, the intensity on the other side, will be equal to the intensity which is going into the polaroid I dash into cos square phi, okay. Now I dash we already know it as I naught by 2 cos 60. Cos 60 is half, right? Cos 60 is half. Half square is 1 by 4, right? This is squared, so half square is 1 by 4, and the intensity is I naught by 8, okay. So option D, I naught by 8, is the correct choice over here, okay. Now that was simple application of Malus law, right? Let's come to the question number 11 over here. Let me see from when it is. It's from 2008, okay. This was from 2014. This is from 2008. Again, a question on polarization, okay, and specifically on polarization by reflection, okay, Brewster's angle. So if you see, when the angle of incidence is 60 degrees on a glass slab, what is happening to me? Okay, so then the reflected light becomes completely plane polarized. then you are supposed to tell what is the velocity of the uh, light in the glass slab. Okay, so that is what you are supposed to tell. Now it's very simple actually. Now some of you might guess it directly because you might know the value of speed of light in your glass, so you might directly say it's option D, right, for those who know it by heart. But this is actually wrong. Okay, so whenever you are faced with a question, please try to do it the conceptual way first. Okay, please try to follow what the question is saying. Don't use your prior knowledge while solving a question. Go in the way the question is directing you to go. Okay, so that is the takeaway point from here. Okay, I'm fumbling too much. Anyways, let's solve it now. So basically here you are supposed to use your Brewster's angle, so 10 IB. Okay, so when the angle of incidence is IB, 10 of IB is given as mu. Okay, refractive index of the denser material with respect to the rarer. Okay, rarer is of course air over here, and the denser one is glass. So we can also write this as C by V, right? Refractive index is basically the ratio of speed of light in vacuum to the speed of light in your particular medium, right? So C, speed of light in vacuum, V, velocity of light in glass. Okay, now 10 IB, 10 of IB. Now IB, we know it as 60 degree, right? IB is the angle at which your incident ray strikes the surface so that the reflected ray is plane polarized. Okay, and it's given that it's 60 degree for the reflected ray to be completely plane polarized, right? So 10 of 60 is root 3. Okay, fine. So we are supposed to find V, velocity in glass. Okay, so V is equal to 3 into 10 to the power 8. So velocity of light in vacuum is this, and divided by root 3. So that gives us root 3 into 10 to the power 8 meters per second, and not option D. So option B is the correct choice over here. Okay, root 3 into 10 to the power 8. Okay, so whenever faced with a question, do it the way the question is asking you to do it, not using prior knowledge. Okay, so let's move to the next question now. So question 12 and 13 over here, these questions are based on an advanced concept wherein you place a glass slab at one of the slits in a YDSA experiment, and there is a shift in the positioning of the fringes. Okay, so basically you are supposed to tell what will be the shift in the central bright fringe. Okay, or basically all the fringes will shift up a certain length when you place a glass slab at one of the slits. Okay, so here we place the slit at S1, and you are supposed to tell what will be the shift in the central bright due to the slab. Okay, so basically the central bright will no longer be formed at this position, which is the center of the center between the two slits. It will be no longer formed over here. It will be formed somewhere above. Okay, due to the part difference which is created due to this slab. Okay, let's not go into the very details of this. You can trust me on that, that the central bright will shift to some other point. Okay, so whenever you place a glass slab, because there is a path difference which is created in the path of this ray, if you can see. Okay, so we can actually use the formula delta x equals d sine theta. Okay, so you are supposed to tell what is this y. Okay, where is the new position of your central maxima with respect to the original position? That is the question. Okay, so we can use delta x is equal to d sine theta, and now take me for the word again, the shift. Okay, the part difference which is created due to a glass slab is given as mu minus 1 into t. Okay, this is a takeaway point. Of course there is a derivation behind it, but it will be too much for today. Okay, so you can take away this, that the part difference created by a particular slab, okay, is given as mu minus 1 into t. Okay, mu minus 1 into t, where t is the thickness of that slab. Okay, and mu is the refractive index of that slab. Okay, now this is equal to d sine theta. Now sine theta, if theta is very small, okay, which it is in most of the cases. You can write it as theta, and you can also write it as tan theta. Okay, so we'll write sin theta as tan theta because it's theta is basically very small. Okay, and tan theta, theta is basically this angle. Okay, the visual angle. Okay, the angular positioning, you might say. Okay, so yeah, so tan theta. So if you see, tan theta is y upon d, right? The opposite upon the adjacent. Opposite is y, the shift, and the adjacent is basically the distance of the screen from the slit, which is capital D. Okay, so tan theta can be written as y by capital D, right? So here you are supposed to find the shift, and shift is nothing but y, right? It is the shift of the central maxima from its original point to some other point. Okay, so y is the shift over here. That is what we are supposed to find. So y is basically given as capital D by small d into mu minus 1 into t. Okay, capital D by small d into mu minus 1 into t. Option B is the correct choice over here. And of course, you can remember this directly as a result. Okay, that shift is capital D by small d into mu minus 1 into t. Okay, and here you are supposed to remember that this is the shift that is created due to a glass slab. Okay, now again a same type of question. Here we are given the numerical values. Here we are given mu, we are given the thickness of the slab. Okay, this is the refractive index, this is the thickness of the slab. You are supposed to tell what is the wavelength that we used for that particular YDSA experiment if the central bright shifts to the seventh bright fringe. Okay, so basically what they did over here is that they conducted the YDSA twice. Okay, and first time they did it without the slab. Okay, so when they did it without the slab, the central bright was formed over here, of course, right? But when they did it with the slab, okay, now they introduce a slab over here in this experiment, the central bright shifted, right? Now this shift was equal to the position where the seventh bright fringe was there in the original experiment. Okay, so basically what they are saying is that the shift will be equal to the position of the seventh dark fringe, right? Or seventh bright, sorry, seventh bright fringe. Now we know the shift, of course. Excuse me. So the shift is capital D by small d into mu minus 1 into t equals. Now the seventh bright spot in case of interference, right? YDSC is interference, so n lambda capital D by small d, n lambda capital D by small d. This is for bright fringe in a YDSC experiment. Okay, now capital D, small d are not changing in both the experiments, right? You do it without the slab or with the slab, right? You're not changing this capital D and the distance between the two slits, right? It is remaining same, so we can cancel it out. And then from here we can easily find out lambda. Okay, n is 7, seventh bright fringe. Mu is 1.6 and 1.6 minus 1 is 0.6. Thickness is 7 micrometer, 7 into 10 to the power minus 6. N is 7 and lambda we are supposed to find 7 and 7 will get cancelled. 6 into, so it will be 6 angstroms, 6000 angstroms. So 6 into, this will be 10 to the power minus 7. Yes, you can multiply 1000, so that will become 6000, and you can multiply with 10 to the power minus 3 to balance, so that will become this in meters. So it is basically 6000, and this is 10 to the power minus 10 meters is angstroms. Okay, so option C, 6000 angstroms is the correct choice over here. Okay, so that's all from the easy category. I know this was a bit advanced concept. Okay, so you have to remember this and this. Okay, this is a particular question, you have to remember this. Okay, shift due to a glass slab. Okay, now so that was all from the easy category. We'll move to the easy to moderate category now. So question 14 over here. Now this is the second last question that we are going to do today. It's from 2018. It's from the easy moderate category now. Okay. So here we are given the data of a YDSA experiment. Okay. You are supposed to tell a position Y where the intensity reduces to half of that at the central maxima. Okay. So now in a YDSA experiment, of course, the intensity goes on decreasing, right? At the central maxima, it's maximum, right? And after that, it goes on decreasing, 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 and then you have the first dark fringe, right? Again, there also it will slightly increase, increase, increase until you have the first bright fringe. Okay, so basically the intensity is varying with the position, right? So you are supposed to find a position where the intensity reduces to half of that at the central bright. Okay, so at the, yeah, at the central maxima. Okay, so basically the intensity equation for your YDSE is given as I equals I naught cos square phi by 2. Okay, so what is my thought process over here? We are supposed to find y, right? So we'll first find phi, okay, from this equation, and then we'll go to from phi we can actually find delta x, your part difference. From part difference we can use delta x is equal to d sine theta, and you can find sine theta. So from sine theta you can equate it to tan theta. Basically tan theta is y by d, right? The vertical position divided by the distance from the screen, right? It's tan theta is y by d. We saw it in the previous questions as well. Okay, now intensity we have to make it half of that of the central maxima. Now central maxima, the intensity is I naught. Okay, here in this equation itself, I naught is the intensity at the central maxima. Okay, and I should become I naught by 2. That is the condition given in the question. So let's find out where, at what phase does this condition holds true. Okay, so I naught and I naught will cancel. Cos square phi by 2 is 1 by 2, or cos phi by 2 is 1 by root 2, right? Taking a square root on both the sides. Now basically phi by 2, you can see that it will be equal to 45 degrees, or pi by 4 I can say, and that 2 you can take it to the other side. So it will become pi by 2. 45 times 2, that is 90, pi by 2, right? So we get the phase angle over here. Okay, so the phase difference between the two waves from the two sources. Okay, now from there we can find this delta x. You might directly know the relation. The thing that I use is lambda corresponds to 2 pi, then this pi by 2 should correspond to what? Okay, yes, what phase difference. Okay, so basically for a phase difference of lambda you'll have 2 pi. Okay, sorry, for a phase difference of 2 pi, the part difference will be lambda. Okay, so so you can use the linear relationship over here, and you can find x will be given as, okay, I'll write it this way. Okay, so x will be given as lambda by 2 pi into, oh, this is pi by 2, right? Yes. Okay, or more generally you can write this equation and you can remember it. Okay, so x is given as lambda by 2 pi into phi. Okay, now phi we already have it as what? Phi we have it as pi by 2. Okay, so pi and pi will get cancelled and we'll have x equals lambda by 4, right? So lambda by 4. So the part difference delta x is pi by 4. Okay, so this is our part difference. So we have found the part difference. What is the next step? Go for sine theta. Okay, so this is a long procedure, okay, but it is a special type of question. Okay, you should remember this. So now delta x we have, we also have d. Let's find sine theta. Okay, so sine theta, in fact we can put it equal to tan theta, right? Let's not waste time in this. So tan theta and tan theta we can in fact put it equal to y by d, right? Because uh, the theta is basically very very small. Okay, and for that condition you can equate sine theta to tan theta, and tan theta we know it as y by d, right? So I've skipped the final three steps. I directly written tan theta as y by d. Okay, now what's the next thing? We know about our um, x. Okay, so we just have to substitute. We want to find y. So y is basically capital D by small d into capital D by small d into delta x. Okay, so capital D we have it as 1 meter. small d is 1 millimeter, that is 10 to the power minus 3. Wavelength, now delta x is lambda by 4. So lambda is 500 into 10 to the power minus 9, it's in nanometers, and lambda by 4, right? So it's by 4, okay? So you'll get 500 divided by 4, 125, and this is 10 to the power minus 9, and this is, so this and that, okay, I can write 5 by 4 as 1.25, and I can merge this two zeros with that, 10 to the power minus 7, and plus 3, minus 4, right? So 10 to the power minus 4, and this will be in meters. Okay, so option B, 1.25 into 10 to the power minus 4 meters is the correct choice over here. Okay, let me uh, just briefly summarize the process over here. First, we found the phase angle using this relation, the intensity relation for YDSE. Okay, we know that the intensity should reduce to half, so it should become I naught by 2. Okay, so from there we found phi. From phi we found out our x, the part difference. Okay, part difference using this relation. We got the part difference. From part difference, we can write delta x is equal to d sine theta. But sine theta is very small, so sine theta is actually equal to theta, or approximately, and which is also equal to tan theta, and tan theta is nothing but pi by d, right? So theta is over here, and y is this distance, and d is the distance from the screen, right? So tan theta is y by d. We use that fact over here and found y from there. Okay, so that is the process that you are supposed to follow, and this is your answer. Let's move to the final question for the day. So question 15 over here, the last question for the day. Then I'll give you your homework question, and then it's time to say bye. Okay, so in this question from 2017, we are asked for the number of bright fringes that will be formed on the screen when we have two sources like this. Okay, now this is also a YDSA experiment, although the slits are side to side and not one over the other. Okay, the slits are like this, I know, but it's still YDSA. Okay, now there is a direct formula for this. So number of bright fringes, okay, BF I'll say, bright fringes, okay, it is basically 2 times of d by lambda. Now I'm putting the square bracket because it is the integer value. Okay, you should focus on the integer value. Okay, so 2d by lambda plus 1. This is the direct formula for the number of bright fringes. Now of course, whenever you are asked for the number of bright fringes, the d will be basically very comparable to your lambda. Okay, usually you'll see d is in millimeters, the distance between the two slits is in millimeters, and whereas lambda is in angstroms, right? In that case, a lot of fringes are formed. Okay, infinitely many fringes are formed, but theoretically of course, but in this case wherein your d, the distance between the two slits, is very much comparable to your wavelength. See, this distance is just twice the wavelength, right? So in this cases, the number of fringes will be restricted. There will be only few number of fringes formed. Okay, so and that number, so for the bright fringes it is this formula. Okay, now let me tell you from where this comes. Just I'll give you a brief idea, we'll not go into the derivation, that will take long. Okay, so d by lambda, so d by lambda is basically the fringe on the above side. Okay, suppose at the center, this is the center, right? Okay, so this is the center. D by lambda of the bright fringes will be formed on top. D by lambda of them will be formed in the bottom. Okay, so 2d by lambda. Now where is that plus 1? Plus 1 is for the central bright. Okay, and here if you see, yes, the distance between the two slits is 2 lambda. 2 lambda, n lambda. N lambda means a maxima will be formed. Okay, so here the part difference is n lambda, and plus 1 is justified. Okay, so suppose this was not equal to n times of lambda, it was some other multiple, then here we won't have a central maxima. In that case, you have to remove this one. Okay, it would be just 2d by lambda. Okay, d by lambda on this side, d by lambda on the other side. Okay, now since we have the central maxima at this position, how do you know that? Because the part difference is n lambda, so of course we'll have the maxima at this point. Okay, So yeah, that is the number of bright fringes. Some of you might have curiosity, what is the number of dark fringes, DF? That does not make sense, but yeah, that will be 2, and then you have to take the integer value of d by lambda plus half. Okay, anyways, we are not asked for this, we are asked for this, we'll do this. So 2, we have to take the integer value of 2 times of d is 2 by lambda, 2 times of lambda upon lambda plus 1. Okay, lambda and lambda will get cancelled. 2 2s are 4 plus 1, and again 4 plus 1 is 5, and integer value of 5 is 5. Okay, so in some cases you might not get integer value 5.3. So basically you have to get only focus only on the integral part. Even if it's 5.9, then just take the integral part, which is 5, not 6. Okay, don't round off. Take the integral part. Okay, greatest integer function, if you know. So option C, 5 is the correct choice over here. Okay, and this is for your dark fringes. You're not uh, a measure of your central bright, so here you don't have to worry about the central bright, you can directly apply the formula. Okay, whereas in this case you have to think whether there will be a central bright at this position. Okay, so that's all from today's class. I'll give you your homework question, and then I'll tell you something new. Okay, so question 16 over here, this is your homework question. You can pause the video here, take a screenshot or make a note. Okay, so that's all for today's class. I hope you enjoyed it. If you enjoyed it, smash that like button and do consider subscribing. Something new is coming up for you in March. Okay, I'll tell you about it in the next lecture maybe, or directly I'll release it in March. It will help you a lot in your BITSAT preparation. So consider subscribing. I'll see you soon in the next video. Till then, keep enjoying physics.